Okay, so let's go, everybody. First of all, I want to thank the Samka, the nanotechnology, for organizing these Thursdays spin-off. And this is the first one we have this year for this course. The title of the presentation today is Precision, Speed, and Scale, DALP or DALP in Advanced Materials Combinatorics. It will be delivered by Michael Mangold, who is now on room. Michael is a chemist and now handling business development at ATLANT 3D. And ATLANT 3D is a spin-off company from the Technical University of DALP means direct atomic layer processing, and it's a platform devoted to the combinatorial material synthesis, which is a kind of new philosophy or new approach to produce many materials with slightly different compositions in a few runs or in a few experiments. So it's a very efficient process. So I want to thank Michael for delivering this talk today. Probably there will be many people attending online, or more people. So at the end, we can have a debate, or you can make questions, and probably Michael will be to answer. Okay. So I will move to the chair, and it's your go. So thank you very much, Michael.
Pleasure. I hope you're hearing me well. Happy to. I am actually going to try to quickly see your. Okay, nice room. Hello, Spain. I am right now based in Berlin, Germany, but I work for ATLANT 3D, which is a company based in Copenhagen, Denmark. And you know why I actually joined this company a couple of years ago. I was working for a large Japanese company, and we were scouting new companies to work with. We were in the ceramic business and like advanced manufacturing. And while I was doing the work, I scouted ATLANT 3D, and then I liked it so much. I said, one day I want to work for the company. So I joined them a year ago, and we are in an exciting journey because we are still validating the science. It's a very new science. And now we have to demonstrate that people want it, laboratories want it, researchers want it, so we can basically exist as a startup and as a commercial company. And that's my goal. So my goal is to help ATLANT 3D be commercially successful now and get more money from investors and so on. So now let's go to the company. ATLANT 3D is a company that was born from, we'll say DTU, but actually 3 co-founders. One is a professor from Germany, and another one is, I think, Slovakia. And basically Maxim, who is Ukrainian, but he was doing a postdoc at DTU. So they founded the innovation, the company, and now we have more than 40 people in the team. Half the team has PhDs and like our scientists, even more than that. Obviously, we complemented it now with the other operational, skills like finance and so on. But most of us are scientists. And the tool that you see on the left is the first machine that we developed, and now we also sold it to University of Vermont in the US. We got investment from Sony very early on. We got collaboration like accelerator program with Merck. We developed a tool for ESA, in a space program project, and we collaborated with Siemens and a couple of others. So now, how many of you, actually I can see you, so you can raise your hand. How many of you are familiar with atomic layer deposition, ALD? Can you raise your hand? Or are you new? Anyone knows ALD? A little bit? Okay, more or less, cool. Yes, so as you know, today we have a couple of thin film deposition technologies, ALD, PVD, CVD, and even in university level, you need to go to the clean room facility. You need to use several machines. Maybe it's ALD, and then you go to lithography, and then you go, to etching. So it's like, first of all, you need to be qualified to go into this clean room. It's intense, and it's not always available. The second issue is that when we want to introduce a new material for a new process, when we want to scale it, right now we're limited by CMOS processes, right? The one that the big factories are using. So in fact, there's only 20 materials each that are used right now for electronics. And if we want to use a new material, that was not used before in microelectronics, you can basically not implement it because CMOS doesn't do it. So it's a problem. So in terms of innovation with new materials for new devices, in terms of prototyping to validate it, today it takes up to 20 years actually to bring an idea from the academic world to a device and make it scalable. And then last problem that we have is that the current processes, ALD, CVD, PVD, and all the other things, you use excess material, excess gas. There's a lot of waste. Etching is like a lot of chemicals. So it's really not sustainable. And we want to change that. We want to change the speed of innovation and we want to make it more sustainable. So here you can see that this is a little bit how it is today, right? It's just what I just said, that you have different steps along the way until you're able to bring that to the market. And the other really the trend that you have right now, and I don't know if this is a topic you deal with, but it's the whole AI material discovery. And actually just a couple of days ago, there's a US White House signed an executive order for the project Genesis, and you can Google it. And it's basically that US want to now leverage AI for scientific breakthrough in material science. It's not just the US, it's a global phenomenon, and that's now available because of LLM. So it's a couple of years old. And now we want to say, well, how can we use it for developing new material? So many companies raised a lot of money, hundreds of millions for AI and algorithm, but actually they cannot print it. They cannot like quickly test it because they are limited still by the current existing methods. So with our machine, which I will explain in more details in a second, you can basically completely almost to the molecule, the nano layer level and the shape and the size and like gradients, whatever, you can basically print whatever the AI tells you. And for the AI material discovery aspect, we are really bridging the gap between the software layer or the algorithmic layer to the physical world, because other machines that are struggling, they're limited in capabilities for the design and the testing. Now, we just talked about DALP. So the founders were working actively with atomic layer deposition, and they were frustrated that you had to wait on the chambers to be filled with excess gas, and then you go to the next chamber, you purge, and then you introduce the next layer. And this is basically how it was in the other ALD machine. Now and I will actually show you this slide is a bit better. We created basically an ALD microreactor where everything happens at the level of the nozzle. So it's a glass nozzle that you can see in the middle here that has like microfluidic channels on a circular shape. And we introduce basically the reactant, the reactor, the inert gas all together in a small nozzle like this and vacuum. So everything here. And that design is enabling us to come close from a surface. You bring that nozzle, you heat the substrate, and then you can locally deposit platinum, titanium oxides, other dielectrics on the surface, and you don't need lithography, you don't need etching, you don't need none of that. So you can imagine other applications for material discovery. You can deposit very quickly 200 different shapes or like sizes or even material composition, and very quickly you can test them. And that was not even feasible before. Any question to DALP, or maybe we pick the question at the end? I go ahead and feel free to, yeah. We can do at the end. I will continue. So it is a nozzle, and the promise of that is not just actually for deposition. There is potential for etching as well. There is potential for cleaning as well, because it's basically we use ALD precursor, which is like a liquid, and then it comes as a gas. So we can use gases, and then we can put the nozzle with the gas, and we can do certain, applications such as etching, such as deposition. So it's really like a multifaceted tools where you can test a lot of different things. And this is like not just a couple of characteristics that potentially we can use up to 450 different materials. And the reason for that is because we can use all the potential ALD precursor. Right now, we can deposit from room temperature to 250 degrees. We have obviously a gas flow. We can basically fully control the way the nozzle works. So we developed a software that can completely program what the nozzle do. And we have optical system to measure that. We can fully control the thickness. We can fully control the shapes and the patterns, and we can control the distance, of course, from the surface. So based on the like if we put the nozzle close, we're gonna get ALD, and actually if you put a little bit higher, you will get some kind of CVD deposition. So we can even modulate that. Yes, and things like this. So this is how it works. This is a little bit the process. So people can design what they want to do. They fill the materials in the machine, in the bubblers. Then they're gonna put the samples in the machine. They're gonna define the parameters, what they want. We do a simulation on the software. It's gonna tell you, well, to get such results, you need to do this and this deposition. Then you launch the job, and then you can basically overnight, you come back the next day, and you have 200 data points of different materials, of different compositions, and so on one single wafer in one single step. So this is not just, again, what I said before. That has all the different like opportunities, the way we can deposit. We can do etching and molecular layer deposition, or even a mixture of both. So we can do deposition and then right after like a cleaning or etching step. So you can basically, I think actually that's the next slide. So you can see in the example of ALE and ALD here on the middle, we can deposit, and then if we want to do a little trench, we can then switch it to ALE mode and make a trench. And as you know before, to do that, you had to fully coat the wafer, and then you had to put in another machine for the etching step. We can do it right away. Because we can control the different materials, you can create doping layers and fully control the stoichiometry. That is also something almost not feasible from before. So that's what we can do. So we can stack material and dope material, control that very with predictability. So now it comes from the resolution perspective. As you can, I don't know if you know, but obviously we can potentially target all the application in the world that requires material science. However, we're still limited by the size. So we cannot go yet into making chips directly because they ask us to print nanometer layers. We cannot do nanometer line deposition because that is extremely difficult in terms of gas physics. However, there's chances we get succeed that in the future. But we can do super well at the moment, 350 microns, 400 microns, which is applicable to a number of applications like sensors, protective layer on certain materials on MEMS. We have now optical application requests for defense and beyond, where we developed a nozzle for 2 millimeter passes, and then we can coat, for instance, certain area to have certain refractive index, or we can go lower, as you can see, up to 8 micrometer. And that was basically a deposition and an etching step of the line to get such small lines. So that's what we did. And the great thing with our tool is that we can control stoichiometry, we can control the pattern, but we can also fully control the thickness. So because we can fully control the thickness, we can create almost perfect gradients, like 5 nanometer at a time, or we can even create valleys of material as you can see it. So we can completely control that. So now, how do we control that? Is because it's like a pen that we bring at the surface. So we just need to come multiple times with the pen, and then you do many passes. So if we just want a small amount, then you just do 1 or 2 passes. And if you want a higher, then you will do multiple passes with the nozzle. And this is how we get, you know, the different thickness. Yes, thickness of the thing. Great. Now, in terms of material, as I mentioned, up to 450 materials, and it comes from this table, which maybe you know as well. It's called atomiclimit.com, where you can find all the different ALD precursor. We, for each material, however, we need to deposit certain materials. We need to develop recipes. That's what I mean. So we need to adapt a little bit the pressure, the gas, the temperature until we find the right recipes for deposition. And this is why nowadays there is 5, 6 kind of fully developed recipes that work really well. And that is like titanium oxide, zinc oxides, magnesium fluoride, platinum. So that's why we develop now use cases in sensors and in catalysis and so on, because these materials work really well now. But we're developing many others that you can see here. And the main reason that sometimes they are challenging is because today we were still working in complete ambient environments like open chamber. And because of this, basically, we cannot work yet with nitride, sulfide, and so on. So how do we control the stoichiometry? So here's an example. As I mentioned, we have gas bubbler, so a bubbler of liquid with ALD precursor, and then we make them come as a gas, and we can control then how the gas can pumped into the nozzle. And by doing so, we can fully control the system and the stoichiometry. And then we can create all the different structures with, you know, you can see here quaternary system and so on. So this is why we can create these libraries. And this is a slide that kind of summarizes what we do. So you can define the parameters and the material. You can develop, like here's an example, I think it was like 200 different lines. And, you know, in a typical, clean room or lab right now, you need one wafer to do one composition. And we can do like now 200. That's the one that you see in the middle. And here you can see that this is a wafer, and you have like, I think around 10 different devices, transistor, we have like a temperature sensor, we have a capacitor, and the whole thing here was printed with multiple materials. And what you see different colors is like a stacking of materials. The shape and the size, the whole thing was printed in one single step in 36 hours or something. Yes. So this is now just one slide again to show the combinatorial material library, how it looks like. So this is like the simulation software, and then you bring it and you can fully control the thickness, and therefore you can control the colors or like different catalytic activity depending on the application, and we can measure that. So now the great things that is coming and is that there was the old way of doing material deposition or material discovery. We had some robotics and it got a little bit better, but now with DALP you can accelerate from 1 to 2 a day or 10 to like 100,000 different deposition a day. And once we're going to combine it with AI algorithm that recommends some certain material or composition, I mean, this will even upscale the whole thing. And this is why we are working now and establishing partnerships with the AI material science firm around the world. So I don't know if that's so relevant to you, but I just want to show you that to commercialize such a technology, everyone wants scale and throughput. So the industry asks us, okay, but can you manufacture things? So we are working on it. This is the one that is already available. And we are now developing a tool where we can connect. It's called a cluster, where the wafer would change like alone. And because of that, then you can start to have some speed and throughput. And this is what we do also, like you can see also on this slide, where you will connect like a metrology equipment and different characterization or XPS equipment, all connected to the tool. So you have the wafer getting in, you get the deposition, and then you can fully characterize it. So everything will be fully automated, and you can get like material discovery will be so fast compared to the way it is today. So that's what we're working on. I'm happy to come back to some slides and explain a little bit deeper. I can show if you have any interest in certain areas like catalysis or or even chip surgery, or you can let me know, and I have specific slides just for that based on our discussions. If someone is talking, I don't hear you.
Maybe you can come to the end. This is the last? Yes. Oh, okay, okay, sorry.
Oh, yeah, no problem.
Okay.
But I have more slides, but basically I have a million slides. So if I get some like triggering, I can show some more slides based on the conversation. Yeah.
So, any questions? Our students have had several presentations about atomic layer deposition, CVD, PVD, so probably they should understand almost everything this technology. So please, feel free to make questions.
Was there a question? I didn't hear.
Okay, I have a question first for you. Producing so many materials at the same time, or just in a short period, is very attractive. But I wonder what happens with characterization. I mean, if my combinatorial material synthesis is probably the drawback of combinatorial materials characterization. So probably if you produce so many different compositions in just a few hours, you need some system to characterize them pretty quickly. So how can you solve it?
No, that's a good point. So basically we have right now an SEM, and I think it's called an ellipsometer in-house. That's our lab, how it looks like in Copenhagen. So we do some of the characterization there. And then if there's other type of characterization, I think refractive index or whatever, usually then we send that to partners where they can characterize it. Many times, we do multiple combinatorial material synthesis for a certain partner, and then they get it back and they will characterize it themselves. So that is it. And of course, for the throughput and to be much faster, this is why we are trying to now work with partners where the full characterization can be directly done connected to the machine. So that is something that we are working on. And this is the slide I think that I was sharing here. So this is where the characterization will be fully connected to the machine. And hopefully in 2 years from now, we're able to do that.
What else recognize? You have some question?
Which is the most complex architecture you can achieve with this technique? Like, for example, the kind of transistors that are being made in researching right now, where the gate is like a tiny pad and are 3D architectures. I wonder if it's achievable with this technique.
I hope I will reply to your question. So this is an example, and we did with partners in Europe as well as Asia. So it's a neuromorphic inspired sensor. And it goes beyond my understanding because it's even physics. But what they did basically is they printed, I think it was like there was a substrate with a certain material. On top of it, they printed a titanium oxide gradient. So it's literally, like titanium oxide then goes down like this. And then on top, they put some kind of platinum. You can see here platinum, titanium oxide gradients, and platinum. And that design enabled some kind of physics to be enabled It's kind of like a brain, like neuromorphic inspired sensor, and they were able to demonstrate higher sensitivity for gas sensing. That is an example that, you know, literally is close to impossible with other type of equipment. So these results, actually, they're going to be published now in a couple of next weeks, and they're presenting it at a conference in San Francisco next week.
I think there is a question from someone attending online. You can read it.
There is a question in the chat, Michael. Yeah, I don't know if you can see it. But,
Oh, yeah, let me see.
Can you read?
What do you think will be the main application of your equipment? Yes, so let me see if I find a slide which I personally like. Okay. So this is a slide showing you all the potential application. It's a platform, right? So it's a 3D printer. It's like your pen in your kitchen. You can cook anything you want, right? So it's basically the same. You can print and you can design and have any kind of devices you want. The real question will be what will be industrialized and scalable in the real world, because on the academic level could be any of that. So there's one area right now that we believe we have high value is in the advanced packaging segment, semiconductors. They have basically a need to interconnect chips together. So they need to connect them. And this interconnect here needs to be very efficient without taking too much heat, because otherwise you have more energy consumption. So we're working on a solution to fill some like platinum or whatever between the different chips into an interconnect. And because we can locally come and we can coat trenches, there is a great application. So advanced packaging is one. We can do completely new sensors, much more sensitive, much more less energy consuming. So sensor is a big area. Third one is the catalytic material in chemical reactions. It can be in microfluidics as well as in microreactors or whatever, because we can locally coat like catalytic material. So we can locally say where and how much material should be printed here, and therefore we can reduce the amount of catalytic material needed for the same activity and catalytic activity. So we can reduce, for instance, 80%. So we have a big area right now of development on the catalytic space for several applications. One example, for instance, is we need to coat right now AFM tip with a specific material to accelerate some kind of sensitivity. So that's kind of an example that we have. So catalysis, sensors, advanced packaging, and we are receiving now as a fourth layer, I would say, a lot of requests in the quantum community, because they are very complex structure. When they need to do their quantum dots, or they are like, sometimes they have to some kind of like nanowire or whatever coated in certain devices. So it's always like very specific like design, and they struggle a lot with existing methodologies. So that's kind of the four. And last but not least, as I mentioned, AI material discovery, which is using the AI algorithm and testing them, which right now no one does.
More questions? I have another question. Do you expect a higher interest in this technology from companies or from universities or public research centers?
Do we speak with them, you said, these different institutions?
No, I was asking if you expect a higher interest among companies or universities.
Yes, let me find you something as well. Trying to find the relevant.
Some of the applications you mentioned are
yes.
very easy to become differences. Some other looks like basic research.
Yes. So these slides shows some different companies here, but I don't have a slide with all our different partners, but I can say it verbally. So NASA bought our first prototype for in-space manufacturing, and we also, as I said, sold our first device to the University of Vermont. We developed the first tool with ST Microelectronics, and we are right now, for instance, working on a pilot for, I think it's a sensor device for Sony. We work on a sensor device prototyping, I think, with 4 to 5 different industrial players. And we are right now catalysis with the 2-3 biggest institutes in the US about catalysis for hydrogen splitting application, as well as some kind of specific masking layer, also some catalysis as well. So that is like kind of verbally what I can say. So big institute in the US, there's big, large corporates. We have high interest from the biggest semiconductor player in Japan because one of the things that I didn't mention is that there's one slide actually that I can add you as well is, let me see if I find it. So we innovate on making devices. So here's like an example where you will use it to have 50 data points in a couple of hours, right? So this is for researcher and R&D, and then they can test it. But another application is that people can also do what is called edge passivation. And this is the example here. So our nozzle is gas, and we can go on the edge of a device, and we can coat on the side and passivate that device. So we did that example on a solar cell, and after annihilation, they could see a higher carrier transportation of electrons. But we can do that also on semiconductor. And so that's a use case right now we're exploring. So it's not just about structure and design, but it's also about certain processes which they struggle to do in the industry. And so it could be solar cell, as I mentioned here, advanced packaging. And we have now some collaboration for the advanced packaging case for edge passivation with some Asian companies.
Thank you. There is another question online. Can you read it?
Yes. How much is roughly your cheapest equipment? So I would say the product market fit is something we're still looking at, but our release price for our tool is right now at 500,000 for the nanofabricator light that you can see here. And then this one will be launched basically actually next week. We have, I think, some kind of demo and launch in California for this tool, and this one is around 3 million. But you know, there is also like the collaboration aspect, so to develop co-IP and so on. So there is like some kind of agreement that we do also with some scientific profiles.
Thank you. More questions? Marin, no one else? Okay, so if there is no question, one of you this conference.
Yes, so I'm just realizing, so we planned that for until 45. I'm just checking, or the whole hour. So how long were we supposed to have more? Let me see.
What?
We have. Yes, I can show you a little bit more. So I wanted to have this kind of interaction already in the middle, but I can share with you a couple of experiments that we've done with the tool. So let me.
Of course.
So this is an example also that they were showing that they were able to control fully the etching. And as I mentioned, the etching for certain application, and it's for advanced packaging and it's for others, they want to have some cavity. And we have an example with an institute in Germany for energy storing application. So they want to fill material in cavities. So this is an example where we were showing that we can fully control the etching areas of the material. If we look now on this one, as I mentioned, we can fully control the height, right, of the deposition. So by controlling the thickness, we were able to create modulation of a surface, and that created, if I'm correct, hydrophobicity. So that is something that we use as a protective layer on our device, like some hydrophobic coating, and so on. This is the example of catalysis. So we were able to control the thickness, and we also obviously control the temperature. And with that, with different deposition, we were shown that we were able to control the crystallinity of the deposition. You can see here like nano island, nano cluster, and so on. So that is also like something amazing. So then people in like 200 data points, right? You can imagine they can see, okay, which one gets, that crystallinity that I want, with the properties I want for a certain catalytic activity. This is to show that we are not so dependent on the flat substrate. So we're able to coat into like rugged surfaces, like a line like this, or like into some kind of channels. That has use cases, for instance, in the bioreactor application or biotech, or as I mentioned before, energy storage devices. This is an example of, if I'm correct, this was the optical, I would keep that. But this one, for instance, is super cool because they control a gradient, and because they control the gradient, I think this one was for some kind of optical applications. Yeah, it's an optical element with different refractive element of the device, and such like fully control like kind of different optical in the same deposition we were able to achieve. And then I want to show another one, which is, yes, this is the hydrogen catalytic behavior. So this, we have now 4 or 5 projects on that. So you know that obviously hydrogen is, many want to have that in the future, but they're still very expensive to produce hydrogen from water. So there is a lot of research to be made to find a way to reduce the cost of the water splitting experiment. So that's why we're working on it. And we use platinum, and you see that she coated 20 nanometer of platinum, and then she demonstrated that we were able to split water into hydrogen by using less catalytic material, which is one of the cost driver, and rare minerals that you don't want to use too much because we don't have enough. Then here you can see that we that was, I think, sensors, electrochemical sensors that you just coat here on the titanium nitride substrate, titanium oxide, and on top you put some lines of platinum, and that is basically creating the sensor. And this is another use case. So when microchip factory, they are producing the chips, but then there is one defect, then the whole wafer basically, or the chip, they can throw it. And because it's very complicated to repair that. So we can come now, depending on the device, of course, and repair locally a defect. So that's a use case we're trying to explore and find partner on a industrial scale. And this one, I think, is what I was mentioning to you, is the etch passivation for, I think, advanced packaging. So to coat on the wall of a material on the side like that, this is like extremely difficult. I know it's feasible, but I think it's like multiple step currently. So we were able to locally control how much edge sidewall we were able to do. As you can see here, 300 micrometer, 200. We were completely able to control that on the wafer edge. And this is I think a protective layer. And if I'm correct, that was, I think it was titanium oxide, but on a MEMS device, fully processed MEMS device with a Bragg mirror. So usually after you make the MEMS, you cannot do anything anymore. But we were able to locally coat a protective layer on the MEMS And we did that a collaboration with Silicon Moss 3 Labs. And after coating it, they tested the MEMS and it was fully functional. So that is again something that was not feasible before, and now we can like do after the MEMS exists, some kind of protective layer. Could be very important for application where failure is not accepted, space application, or you know, very important automotive kind of vehicles. You don't want it to fail, so you want to make it even better. This is a use case actually, which is interesting, but even the luxury industry or defense industry can benefit from. When we control the thickness of a certain material like titanium oxide, you change the refractive index, and therefore you change the color of the material. And we can control the color basically because we know the deposition, we do the thickness, we check, and then we will able to print different colors. So luxury industry wants it. We're actually working right now with luxury players from Switzerland, where we will print on certain of their device, like different colors and shape. Because today, if I want to do that with metal, they actually do multi-steps PVD, and it's kind of complicated. And especially if the surface are very small, or they need to be very precise. So that's kind of where we work on. And there's the same demand for like a defense, where they are asking for certain areas to be coated for having a certain reflection or kind of invisibility kind of thing. So we can control that as well. Yes. So that's kind of ideas and brain for thought that you can think about. We started to put this machine in the hands of people. So that's very new, right? A couple of months old. So we're very excited what they do with it, because it's based on their expertise. And there's a person in Erlangen in Germany. They printed a fully functional solar cell from one step. Like they literally just did the full solar cell. That is something we didn't do. We didn't think about doing, and they did it. And now in the US, they are working on new battery types and new electrodes and things like that. So yeah, possibilities are really unlimited.
Okay.
Yes, and with that, I think if I'm correct, I'm not sure where you all are in your career, or if it's PhD or master or postdoc, but whenever you have ideas of the groups you work on and you would like to do some local deposition for a certain application, feel free to come to us and we can chat about different collaborative possibility.
Okay. Good. More questions or comments? No other example from your side? Okay, so if this is the case, I think it's time to finish. So thank you very much. Thank you from Jose Maria, one of the persons attending online, and thank you from all of us.
Thank you very much. Feel free to connect also with me on LinkedIn if you want. My name is, I think, Michael Mangold, right? We can stay in touch, and for other stuff, not just ATLANT 3D. I'm very involved with the startup ecosystem. I live in Berlin. If you come over, let me know, and we can stay in touch.